Hello everyone, Paul here with the review for the astronomy test. What I'm going to do is basically just go through this review sheet and show you in these notes over here where the answers to the questions on the review sheet are, just so we're all sure that we're studying the right stuff. Okay, before I begin that though, let me just show you this. This is a chart of each of with the names, obviously, of each of the planets and their distances to the sun. You're going to want to know this for the test for a variety of reasons I've talked about in class, but for right now, just know that for the test, it will be very, very handy. This chart is in the astronomy module. It's down in the supplemental materials area, along with a couple other things you might find useful. So anyway, there's that. All right, let me close that. And so, like I said, what I want to do now is just basically go through the review sheet. Just make sure we all have the right answers for things. Okay, so we begin with number 1, which is naming the major astronomers in the Western tradition, too far, and describe each of their contributions. Now, I'm not going to go through each of the astronomers. You all know what I'm talking about, I think, but let me just come over here. And what I'm talking about here is Copernicus, all the way down through Galileo and then Isaac Newton. So there are the astronomers that I'm talking about there. Now, as you study these, what you want to do is make a flashcard, either a physical one or a virtual one, however you do it. Put the bullet points on one side and put the name of the astronomer on the other side. And then run them looking at the bullet points and naming the astronomer. I'm not going to ask you, what year Nicholas Copernicus died or something like that, right? I'm going to describe what the astronomer did and ask you to name them, right? And so if you know what they did and you know who did it, you're good to go. All right. So that's how you want to study the astronomers. Bullet points on one side. Name on the other side. Look at the bullet points and get to their name. All right. Okay. Questions 2, 3, and 4 are all about retrograde motion. And so the first question is, what is retrograde motion? And what retrograde motion is covered right there. Retrograde motion is when a planet looks like it's moving, quote unquote, backward. So planets will move across the night sky night after night after night, and then every now and then they will reverse their direction, and then they will go forward again. Now, this isn't like, rising and setting. This is like watching at midnight the same time every night, night after night after night. They seem to move among the stars, which is why they're even called planets, okay? Retrograde motion is when that motion reverses itself and they're moving backward. For example, in the case of Mars, it moves backward for about 80 days or so, and then it turns around and moves forward again. So that's what it is. It's just the observation that that planets move across the night sky, and then sometimes they turn around and go backward. What causes this? Well, what causes this is we're passing the planet as we go around the sun, or the planet's passing us, but we're passing the planet as we go around the sun. So it looks like we're moving backward, or they're moving backward, it's moving backward, when it's really not. Okay, it's kind of like passing someone in your car, right? At that point at which you're going by them, it looks like they're moving backward, but they're not. You're just moving faster. And then question 4 asks, why does the Ptolemaic system need these epicycles along its orbit, right? And remember that the epicycles are these smaller little suborbits, right? Where if you watch my mouse here, the planet goes, let me see if I can get a pointer. I can't. Okay, I can't over there. The planet goes like this. I'm right in the middle of the screen. The planet goes like this as it goes around the Earth, right? Ptolemy was a geocentrist, right? He thought that everything went around the Earth. And so what these little epicycles do is they make the planet seem to be moving backward from time to time as it goes around the Earth. So these epicycles are Ptolemy's way of explaining retrograde motion in a geocentric solar system. right? And so, because he can't think we're passing the planet as we go around the sun, because he doesn't think we're going around the sun. He's dead wrong, but he did it very well. And so that idea would remain influential for a very long time. So there's 3 questions about retrograde motion, and there's their answers right there under the Ptolemaic system area there. Okay, so state and explain Kepler's 3 laws of planetary motion. And so they're going to be right down here underneath Johannes Kepler. And here they are right here. I already highlighted them when I highlighted Johannes Kepler and the astronomers, right? So the first is that the path of each planet around the sun is an ellipse, with the sun at one focus and the other focus is kind of out there at space. This is important because understanding the shape of these planetary orbits allowed Johannes Kepler to accurately predict planetary positions, right? And so, yeah, so the second one sounds funny. Each planet revolves so that an imaginary line connecting it to the sun sweeps over an equal area in an equal interval of time. This is just saying that, look, hold on, I'm going to find a drawing and I will be right back with it. Give me 1 second here, guys. Okay, I'm back with a drawing. So what Kepler's second law is saying, look, it actually states if I run an imaginary line from the planet to the sun, it will sweep an equal area in an equal interval of time, right? So what Kepler is saying is, look, with this planet's elliptical orbit around the sun, that's his first law, if I run a line from the planet to the sun, if it takes a month to go from here to here over on the left side of the sun now, and a month to go from here to here on the right side of the sun now, right? As long as the time to go from here to here and here to here are the same, the areas will be the same. So this area and that area are the same, right? This dimension shrinks, this dimension gets bigger, they offset each other perfectly. That area and that area are the same. Okay, so if you see a diagram on the test that looks anything like this, the correct answer is the areas are the same. Okay, I'm not going to try to find some weird drawing or something like that. Okay, so there we are. Okay, back to this, and if we look at Kepler's third law, we see that the orbital periods of the planets and their distances to the sun are proportional. So the further you are from the sun, the longer it takes you to go around the sun, right? Mercury takes 88 days to go around the sun. We take 365.25 days to go around the sun. I think Neptune takes 165 years to go around the sun. That would be Earth years to go around the sun. That's all that says. So yeah, you probably walked in here knowing that already. Okay, so that's Kepler's 3 laws of planetary motion. They're right there underneath Johannes Kepler in the notes. Okay, so then we get some definitions: rotation, revolution, solar day, sidereal day, aphelion, perihelion, and precession. So let's go down here. Rotation is the Earth spinning, right? Roughly once every 24 hours, but that's rotation, the Earth spinning. Revolution is the Earth going around the sun. Okay, I know I give you some numbers here. Don't worry about them. Just know that revolution is the Earth going around the sun. Rotation is the Earth spinning on its axis. Then we have a solar day and a sidereal day. And that's going to be, right up right here under rotation. So there they are, right? A solar day, remember, is the time from one solar noon to the next solar noon. A sidereal day is the time that it takes for the Earth to complete one rotation, one time around, right? And we went through this whole thing with an animation, but remember that they're different just because the Earth is going around the sun. So the time that it takes to go from noon to noon ends up being different than the time it takes to go around one time. Okay, solar day, sidereal day, aphelion, perihelion, and precession. Okay, so aphelion is, here they are right down here. Aphelion is that point where the Earth is furthest from the sun. Remember, the orbit is an ellipse, so there's going to be a point where it's furthest from the sun. Perihelion is that point when the Earth is closest to the sun. So there those two are. And then precession is down here. And so this precession is the movement of the Earth's axis of rotation, right? So if you imagine the Earth spinning kind of like a top where it's leaned over and it's moving around, the axis is moving around, right? That's precession. The Earth's axis is tilted 23.5 degrees relative to the plane of the ecliptic, and so that the axis moves. It swirls around like a top. And once again, that is called precession. So let's make sure we got them all. Rotation, revolution, solar day, side day, real day, aphelion, perihelion, and precession. I'm going to be honest with you. I'm not too worried about 7 and 8. I'm not going to put these diagrams on the test. If you just know, sorry, the definitions of a solar and a sidereal day and the definitions of a sidereal and a synodic month, you will be just fine. Okay, so let's go down to 8 and make sure we get the two different kinds of month, right? And they're right here. And so we have a synodic and a sidereal month for the same reason that we have a solar and a sidereal day, okay? Because the Earth and the Moon are going around the Sun. And so a synodic month is the time from one new moon to the next new moon. That's the kind of month that we're mostly used to, roughly 30 days, 29 and a half days. And then a sidereal month is the time it takes for the moon to go around 360-degree time, okay? And they're different because the Earth and the Moon are going around the Sun. And if you're not really clear on that, find it in my lecture or ask me, and I'll explain it again. But yeah, so don't worry about drawings. Just worry about definitions for those, and we'll be just fine. Okay, what causes the phases of the moon? That's question number 9. And so here it is right here. Phases of the moon. Half the moon is always lit. But as the moon goes around the Earth, the portion of the lit half that we can see changes, okay? During a full moon, you can see all the lit half. During the new moon, you can't see any of it, okay? And I went through that whole thing with that lunar phase simulator. There is a link to that lunar phase simulator, I believe, in the supplemental materials submodule in astronomy. If you want to play around with that a little bit, or for whatever reason that doesn't make sense, let me know. All right. And then we have eclipses. We have a solar eclipse and a lunar eclipse. Okay. And so that's question number 10. I say what causes the eclipses here for 10. Mostly I just want you to be able to describe them. And so there they are, right? And so for a solar eclipse, you have the moon blocking the sun, casting a shadow on the Earth. For a lunar eclipse, you have the Earth blocking the sun, casting a shadow on the moon, right? And so, you probably want to make sure that you know the order of these things, right? And so, for a solar eclipse, you're going to have sun, and then moon, and then Earth. For a lunar eclipse, you're going to have sun, Earth, moon, right? And so think about what order these things need to be in order to get that to happen. So yes. Now, then question 11 asks, why aren't there 2 eclipses per month, right? So in other words, as the moon goes around the Earth, it feels like it should, once a month the moon should pass between the Earth and the sun, and then once a month the moon should be on the other side of the Earth in its shadow. And so it feels like we should get a solar and a lunar eclipse every month, and we don't. And we don't because this first sentence right here is the key sentence, right? The moon's orbit is inclined 5 degrees relative to the plane of the ecliptic, which is the plane that the Earth orbits in, right? That means that it usually doesn't line up. Usually the moon's shadow misses the Earth's shadow misses the moon, etc., etc. So there we go. Okay, so that's that first chapter on the history of astronomy and on motions of the Earth and the moon and other bodies like that. Okay, moving on to the solar system. So first of all, we talked about differences between terrestrial and Jovian planets, and here they are right here. Ooh, kind of outlined. Let me see if I can do that without scrolling quite so much. Maybe not. There we go. So there they are kind of outlined. Remember that the terrestrial planets are the Earth-like planets and the Jovian planets are the Jupiter-like planets. So terrestrial planets are Mercury, Venus, Earth, Mars, Jovian planets are Jupiter, Saturn, Uranus, and Neptune. Terrestrial planets are small, Jovian planets are large. Terrestrial planets are closer to the sun and more dense because they're made of rock. Uh, Jovian planets are bigger, they're further from the sun. They're less dense because they're made of gas and ice and stuff. All of the Jovian planets have ring systems. None of the terrestrial ones do. Terrestrial planets don't have a whole lot of moons. Jovian planets have a whole lot of moons. So there we go. So, the eight classical planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, the first four are terrestrial, the last four are Jovian. And so we have two very distinct divisions there. Question 13, ignore it. Just ignore it. Don't even, I'm going to just don't do that. It's something I used to talk about. I don't talk about it anymore. So just ignore that question. I'm going to even like highlight it in red. Just ignore that. Okay. Oh, I did have to say this. Name the planets in order from the sun out, right? That's that chart that I showed you. So make sure you can do that. Also make sure you know how far they are from the sun. They are in the notes in order. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Okay? Okay. Then we have some definitions with respect to the moon. So crater, Maria, regolith, Highland. And so here we go. So let's come back up here and let's see. Crater, so blah, blah, blah. Features. There they are. Here we go, right? Craters, big holes that form from impact. Okay, impact used to be a lot more common, but that's what they are. Lunar highlands are mountain ranges on the moon. The moon does not have plate tectonics, okay, but impacts will pile up material and rock and make mountain ranges. These are also the oldest parts of the moon. Maria are lava flows. That's the dark areas you see on the moon. These are also caused by large impact events that cracked the crust and allowed lava to come up through those cracks. Regolith is just lunar sediment, moon dust. It covers everything. It gets on everything. It sticks to everything, apparently. So there we are. So there's our features of the moon. Then I ask, okay, why does the same side of the moon always face the Earth, right? Because no matter... oh, is it not in the notes? Oh my gosh, it's not in the notes. Okay. Hold on. Nope, it's not. Okay. How weird. I'm gonna. Nope. No. Oh, there it is. There it is. Yay. Just to know where in the notes. Same side of the moon always faces the Earth, right? No matter what. No matter how much of the moon you're seeing because of the phases, you're always looking at the same side. And that same side always faces the Earth because, quite frankly, it's just heavier. It's got all the lunar Maria on it, and so our Earth's gravity has grabbed a hold of that, yanked it toward us, and so that same side always faces us as the moon goes around the Earth. Because of this, the moon's period of rotation and its period of revolution are the same. Takes it, 30 days to go around the Earth, takes it 30 days to spin one time. So that same side always faces us. And then, okay, so 17 talks about what you want to know for each planet. And basically what I'd like you to do is treat the planets the same way you treated the astronomers, right? You want to make flashcards with, bullet points on one side and name on the other. Okay, and what I will do is I will describe the planet and then I will ask you what planet I'm talking about. Okay, I'm not going to ask you what the average nighttime temperature on Mercury is. I'm going to say, its smallest planet, blah, 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 blah. Which planet am I talking about? And you pick out the answer that says Mercury. Okay, so there we go. Okay, I'm going to go ahead and highlight these because I want you to know them. And so here we are. My monitor's doing weird things, but that's okay. There we go. So there we are. Okay, so once again, same thing for each of them. Just be able to recognize the planet when I'm talking about it. Okay. All right. So that's that. And so now what we want to do is light and the sun. And so how do we know light is a wave, and how do we know light is a particle? Okay, so we scroll down here, and I do have a nice little summary thing, and that is right here. Light is a wave and a particle. There it is. Seems a little bit anticlimactic after all we talked about it, but there's the fundamentals, right? Uh, as far as a wave goes, light refracts because it's a wave, right? It bends as it goes from one medium to another, from one thing to another, as it goes from air to water or air to glass and glass to air or whatever. It bends, okay? That's that refraction. It does the Doppler effect because it's a wave, right? A light source moving toward us will detect at a lower wavelength than a light source moving away from us. You won't actually see the difference, but a fancy instrument can pick it up. Right? And that's where we talked about how um, all the other galaxies that we see are redshifted except for the Andromeda galaxy, which means they're all moving away from us, which is a kind of handy thing to know. Particle, two things, the photoelectric effect, right? The idea that light particles hit things and knock electrons loose. That's the photoelectric effect that Einstein kind of explained. Um, and so, yeah, light needs to be a particle for that to happen. And then comet tails. Comet tails always point away from the sun. That's because all the light now coming off of the sun is behaving like a particle. The light, all the radiation, the light, just all of it, is hitting that comet and knocking that stuff off of the backside. And so you end up with a comet tail that doesn't point behind the comet. It points away from the sun. Okay, so we have a few things here, getting a little bit deeper into that, but let me say this. Do not worry about number 20 because just don't. Yeah, I'll do it that way. Because that's, really all I want you to know about the photoelectric experiment is that it shows us light's a particle, and that's up there under 19. So, meh, not too worried about it. How are different wavelengths of light refracted, though, is important. If we come back up here under refraction, there we are. Different wavelengths of visible light sorry, I'm looking for it. Here we go. Yes, here we are right here. Right there. Because light's a wave, it refracts. Now, here's the trick, though. Shorter wavelengths refract more, longer wavelengths refract less, right? So blues and violets are going to bend more as they go from one medium to another. Reds are going to refract less, right? And so that's what makes rainbows, right? That's what breaks out the different wavelengths of light, is because those different wavelengths refract at different angles. All right, so there's that. Um, okay, so then we have different kinds of spectra, a continuous spectrum, an absorption spectrum, and an emission spectrum, right? And so those are right here. So there we are, and let me go ahead and do that, and yes. So there we go. Okay, so a continuous spectrum is when you have all the wavelengths of light present, right? You're making a rainbow. You got all those different colors broken out because those different wavelengths refract at different angles. So then a dark line or an absorption spectrum is what you get when you pass the light through a cool gas, right? You pass it through a cool gas, that gas absorbs certain wavelengths of light. So what comes out the other side is a rainbow, but with little black stripes in it because you're missing certain wavelengths of light because the gas absorbed them. Okay, and then if I heat that same gas, right, it will glow, which means it's emitting light. And if I pass that light through a spectrum, what I'll get is just some bright lines there, right? Just the opposite of a dark line spectrum. Right? A bright line spectrum, rather than missing a few wavelengths of light, you only have a few wavelengths of light. Okay, and so, and in both cases, if you don't know what the gas is, you can identify them based on the spectra. And, just look at either what you're missing or what you have and use that to identify the gas. For every given gas, what you're missing and what you have will actually be the same thing. Whatever you're missing when the gas is cool, that's all you will get when the gas is warm, okay, or hot. Okay, so those are our three different kinds of spectra. Then I asked, what is the Doppler effect, right? And so the Doppler effect is a shift in an apparent wavelength, um, because the thing making the waves is moving. It also works if you're moving, by the way, but let's keep it simple. The thing making the waves is moving, right? Sound does the Doppler effect, which is why the pitch of something will seem to change as it goes by you, okay? But light also does the Doppler effect, right? And so things moving toward you are shifted toward the shorter end of the wavelength spectrum. Things moving away from you are shifted toward the longer end, right? And so anything moving toward you will be blue shifted because that's the shorter end, okay? It's not going to literally look bluer, but if you have a fancy instrument, you can detect that blue shift, okay? And then things moving away from you will be red shifted. Once again, it doesn't look red. It's a fancy thing that you have to use a detector for to work it out, okay? So anyway, so things moving toward your blue shifted, things moving away from your red shifted, because of that apparent shift in wavelength, because something is moving either toward you or away from you. The Doppler effect, question 26 asks, why is the Doppler effect important in astronomy? Well, because first of all, it'll tell you if something's moving toward you or away from you, which is a very handy thing to know. The other thing is that the Doppler effect tells us that the universe is expanding, right? And that when we look at other galaxies, they're all redshifted except for the Andromeda galaxy, which is the one that is closest to ours, and it's blue shifted. It's moving toward us. Okay, but every other galaxy is redshifted. That tells us the universe is expanding. If you run that backward, the universe is contracting until a point about 13 billion years ago, when everything in the universe was at the same place in time, and then it exploded, and that's called the Big Bang, which is a horrible name for a very complicated idea, but it's fundamentally very simple. If everything's redshifted, it's moving away from us. If you run that backward, it's moving toward, everything is moving toward everything else. And so what happens when everything gets to the same place in time, and weird things happen. So anyway, but the Doppler effect kind of leads directly to, the idea that the universe is expanding. Okay, let's see. So moving into telescopes, we have a question about the difference between a refracting and a reflecting telescope, question number 27 there. And so it's pretty simple. A refracting telescope will use a lens to gather light. A reflecting telescope will use a mirror to gather light, right? And so there's that right there. Refracting telescopes use a lens, and reflecting with an L telescopes use a mirror. And so there we are, and there we are. Okay. Let's see. Too far. Difference between, yeah, okay. We got 27, 28. What are the three main properties of a telescope? Why are they important? So here they are right here. Light gathering ability, right? Which is, the ability to gather light. I think y'all understand that, though. This is the most important thing a telescope does, and it is a function of the size of the lens or mirror. Bigger is better. Bigger lenses, bigger mirrors gather more light. Resolving power is basically how sharp is the focus. The problem with resolving power is a lot of time problems with resolution have to do with our atmosphere, which is why we put telescopes in orbit, right? You get them out of the atmosphere, you don't have that problem anymore. And then magnifying power is the ability to make things seem larger. This is what people think is important about a telescope. It's not. The light gathering ability is what's important. But magnifying power is important too, but you can change it. You just change out the eyepiece on the telescope and you got it. You're done. You're there. So it's not that hard to do. Certainly not something that's just built into the telescope that you're stuck with forever, because you're really not. Okay, there we are. Now, turning our attention to the sun, we have three layers: the photosphere, chromosphere, and corona. And so let's skip the interior for 1 second. Here's the photosphere. This is the surface, quote unquote, of the sun. About 10,000 degrees Fahrenheit. Most of the sun's light. It's about 300 miles thick with a pressure of about 1/100th of our atmospheres, composed of granules, etc. I will probably treat this the same way I treat the astronomers and the planets. I'll describe a layer, you name it, right? Let's see. We might come back to sunspots. I don't know. A photosphere, chromosphere is right here. It's right above the photosphere, and it's got these gas jets in it called spicules that are coming up from the photosphere of the sun. And then the corona is the outermost layer of the sun. This is that white haze that you see around the sun during an eclipse. Temperature goes up to about 2 million degrees Fahrenheit. Um, the corona, the outermost layer of the sun. Okay, so there's the three layers, and then we have solar flares and solar prominences. Solar flares are up here. These are explosions of radiation associated with sunspots off of the surface of the sun. Solar prominences are explosions of ionized gas. Okay, so there's two different kinds of explosions on the sun. Yeah, and what was I in? Blah blah blah. Two different kinds of explosions on the sun. Oh yeah, so on the test, what you want to do is look. If I'm talking about explosions on the sun, and I say radiation, that's a flare. If I'm talking about explosions on the sun, and I say ionized gas, that's a prominence. Okay, that's how you tell them apart. And then I ask, how does a proton-proton reaction create energy? And that's actually up here in the solar interior, right? And so what happens here is, I'm going to put it right here. And so there we go, right? Highlight it. There we go. So you take 4 hydrogen atoms, you squeeze those into 1 helium atom. When you do that, you have a little bit of mass left over. Mass does not like to hang around, not part of an atom, right? You just have a random mass floating around out there. That's not going to do. And that mass, under those conditions, will snap itself straight into energy. Doesn't take a whole lot of mass to make a whole bunch of energy. It really doesn't. And so the sun is burning like 700 million tons of hydrogen per second or something ridiculous like that. So, okay, there we are. So there's review. I am going to send out this highlighted version of this review sheet in the email saying that I got the review up so that everyone will have it. And then hopefully that will help you all study for the test, okay? Okay, all right. I'll send this out and I'll get this uploaded to YouTube so y'all can watch it. Y'all take care. I'll talk with you later. Okay, bye-bye. Let me know if I can help. Okay, bye-bye.